So for me, this is the punchline of what we've been doing the last couple of videos. I mean, the Veblen hierarchy is really cool, and it's it's a very important way to think about relatively large ordinals. But for me, the goal was always to come back to the fast-growing hierarchy and produce new finite numbers. So let's do a notation switch. We used to have the label of which function we were talking about as a subscript, and then the input over here. Let's actually put them on an equal footing, because the label here is going to get super complicated. I don't want to hide it in a subscript. It'll just be too small. Okay. So here's as far as we went before. We were looking at the epsilon naught rank function of the fast-growing hierarchy, and we just put in 3. And I showed you a little bit of the expansion of that and how incredibly huge it's going to be. So that's really f of, now in our new notation, phi1 of 0, comma 3. So it's it's almost the dinkiest Veblen, the second dinkiest Veblen function, the first value of it, or the 0th value. And that was already unbelievably huge. Okay, so now let's just look at a little bit of explicit expansions of what happens if we take f of, let's say, phi2 of 0, comma 3. So phi2 of 0, remember, was the thing that kind of took epsilon sub epsilon sub epsilon. So I'm gonna try to stay mostly within the phi language to give us practice with how the phi expansions go, but occasionally I'll go over to the epsilon language and a little more explicit. Okay, so f of phi2 of 0, comma 3. Remember, our rule is when this is a limit ordinal, and it's almost always going to be a limit ordinal, we diagonalize, and so we just look at the third element in a fundamental sequence that sneaks up on phi2 of 0. Okay, well, that was phi1 cubed of 0, comma 3. Okay, so we can express that various ways. It's going to be very helpful to break out just one of those phi1s, so phi1 squared of phi1 of 0, or in other words, phi1 squared of epsilon naught, or in other words, phi1 of epsilon naught. If you want to do it in terms of epsilons, it's epsilon sub epsilon sub epsilon naught. So it's this very clever thing about epsilon numbers that you can nest them. Okay. So, but what if we just stay with the Veblen stuff? Phi1 of 0, by definition, that, well, let's see. Let's look at this. We first need to remember how the fast-growing hierarchy works. Okay. We've changed this guy to a smaller ordinal because of the diagonalization trick. But now we're going to do it again. We want to take the third element in a fundamental sequence for this guy. So we have to unpack it from the outside in. This is phi1 of something. And remember, whenever you put anything that's a limit ordinal into these guys, you just look at the fundamental sequence for what's inside. So what that means is no matter how many phi functions we have on the outside, we're going to sort of pass this 3 instruction deep inside the stack to the innermost level and say, okay, do I have something that I can repeat 3 times? Okay, so what we're going to do is we end up having the third element in the fundamental sequence for phi1 of 0. That's phi naught cubed of 0. And these guys are just hanging out, ready to be evaluated eventually, although we'll never actually get to that. Okay, so now, okay, this is phi1 squared of phi2 squared of phi naught of 0. Oh, for God's sake, that's actually 1. We actually can evaluate that. Okay, so phi1 squared of phi naught squared of 1. Okay, and let's just break that out a little bit. Phi1 squared of phi naught of 1. Just make it more explicit. Phi naught of 1 is omega. And so phi naught of omega is omega to the omega. So we could just write this as phi1 squared of omega to the omega. Okay, so we're making some progress here. But let me just stay with the phi stuff as much as possible. So let's see what we got. We got phi1 of something, and we're trying to find a fundamental sequence. So we pass that inside. And then another phi1 of, that's the 2 layers of phi1. Then we got a phi naught of something, and this is still a limit ordinal. Okay, so we just pass that 3 instruction all the way in, and we say, oh, the third element of a fundamental sequence for omega, that's just 3. That's easy. Okay, so now we're getting somewhere. Phi1 squared of phi naught of 3. Oh, phi naught of 3 is just omega cubed. Okay, that's easy. It's omega exponentiation. So now we've still got to pass that in. This is still a limit ordinal. As long as this is a limit ordinal, I'm just going to basically keep hacking away on the inside here and demoting it to the third element of its own fundamental sequence. Well, the third element of the fundamental sequence for omega cubed is omega squared times 3. That's still a limit ordinal. That's omega squared 2 plus omega squared. That's how we work ourselves up to... Oh, that's just exactly the same thing. And now I just take the fundamental sequence. omega squared times 2 plus omega times 3. I'm demoting the omega squared to its fundamental sequence. That's still a limit ordinal. I'm going to demote that. Finally, I get a successor on the inside. So I've got phi1 squared. I still have 2 powers of phi1 left to be evaluated, of omega squared times 2 plus omega times 2 plus 3. Okay. Now I need to figure out how to work with that. So now I'm going to split the phi1s apart. Phi1 of a successor ordinal. How did that work? How did the fundamental sequence for this part work? The phi1 here is just, I'm just passing through that because this guy is a limit ordinal. But this phi1, to get the fundamental sequence of that, I actually have to go back to the rule. And remember, the trick was I take phi1 of the previous value, just with a 2 here. I do the +1 trick to get out of the fixed point trap, and then I apply the previous phi function 3 times, phi naught cubed. Okay. And then that's going to keep going. I now have phi1 of another successor ordinal. I'm going to demote that and do the +1 trick, but I'm going to pop out another phi naught cubed on it. And then I'm going to do it again. And then I'm going to start hacking away at the omega 2, and then eventually I'm going to hack away at the omega squared 2. Something to notice here is that all I've been doing so far is expanding out the subscript. I have not gotten to the stage where this is actually a successor ordinal, and I actually start repeating and start doing the functional powers of the f functions. So before, even with epsilon naught, I eventually got to an expansion where I started doing f sub this of f sub this of f sub this, and I've got a huge stack of repeated versions of f. That's going to happen eventually, but with these guys, they're already so big. Even at phi2 of 0, they're already so huge and so complicated that just to unpack the subscript is going to give me a huge thing. This keeps going for quite a while. Okay, this keeps going for quite a while before even the subscript gets unpacked. Okay, and I'm really not going to actually show it explicitly. In fact, even for this one, it might actually be so big that it would take an ungodly huge number of lines to even unpack it, even if I put lots of summary ... dots in. Okay, but you know, if that's too hard, let's make it harder. What the heck? Why not? Let's get a little bit of a feel for how phi sub omega of 0 would unpack. Well, the first step is it just goes to phi3 of 0, so that's not going to be super different from phi2 of 0, but that's going to be phi2 cubed of 0. So that's going to be phi2. I'm going to leave these two open and expand the phi2 as 3 phi1s. And then finally, phi1 of 0, just like I had up here, the phi1 of 0 is going to unpack with a few steps to be something like this. That's an unpacking of the omega cube that we're going to get out. Okay, and then the same thing's going to happen. Notice I've got the phi1 of this expression in both of these guys, and I'm just going to unpack it. The difference is here I've got an additional phi2 of phi2 of all this stuff. So here it's gargantuan enough to expand out phi1 of this guy. Now that's put into 2 phi2s, and every time you expand a phi2 you get something like this. It's just going to be ridiculously huge. So the moral here is not too surprising, because the Veblen idea, remember the Veblen idea of these recursion and diagonalization ideas, was that to create new ordinals in a way that somewhat matches the fast-growing hierarchy, it means that just the expansion of the index, what used to be the subscript here, is going to be basically as complicated and huge as was the fast-growing hierarchy itself. And then we're going to take, once this is finally expanded, and this finally gets to be a successor ordinal, eventually, we're going to start using that as instructions for iterating the f. It's just unbelievable how big that's going to be. It's really kind of hard to imagine directly, but it's cool to think about. Okay, what about one last one explicitly to some degree? And I actually did more work to expand this one out, so take a look and just kind of let your eyes glaze over a little bit, but you can do it yourself if you want. F sub epsilon naught, f of phi sub epsilon naught of 0, comma 3. Whew. Okay, let's see. This is a limit ordinal, and so you just expand it as omega to the omega. Oh, how bad can that be? That's not that far bigger than omega, right? Well, now we've got a non-trivial limit ordinal in the subscript of the phi, which itself, this whole thing, used to be the subscript of the f. Wow. Okay. So something we've seen a lot before when we've got a 3 here. This just basically expands out as omega squared 2 plus omega 2 plus 3 after a few steps. Okay, so that's a successor ordinal. So that expands out in terms of multiple copies of the previous one. And then this, I'm just going to expand the inner one only for now. And that expands as 3 copies of the previous one. And then I expand that inner one only, just this guy, and that expands as 3 copies of the previous one, etc., etc. Okay? So what you get, let's go down to here, you get f of this whole thing is this, what used to be the subscript of the fast-growing hierarchy. It is a huge nested sequence of 2 copies of each phi function with the subscripts of those guys going down from omega squared 2 plus omega 2 plus 2 all the way down in a sequence that we've sort of seen before, down to omega, and then further down to 3, and then down to 2, and 1, and 1, and finally we can expand that out as an epsilon. Okay, if we want to. We could even go further in terms of omegas, but I decided to go into epsilons for this version. Okay, so now phi 1 squared of epsilon naught. Ah, that's a familiar one. That's epsilon sub epsilon sub epsilon naught. Okay, and then we got phi 2 of that. Okay, but we still need to take some fundamental sequences. So in fact, the 3 here actually does eventually destroy this epsilon naught, demote it to omega to the omega. Okay, so there is actually some work still to be done on this that erodes it a little bit. Okay, at this point I just stopped and I said, wow, because remember, all these dot dot dots hide a fairly large number, not unbelievably huge, but a fairly large number of additional phi functions iteratively applied to this thing, which is already unbelievably huge. Okay, if you continue with the phis more and try to stay away from the epsilon number notation, you can actually keep expanding. So we've got all these phi squareds with all these different indices of omega to the omega. Then you can expand this guy out because it's still on the inside. It's still a limit ordinal. We can still expand it out. Ah, but now it's a successor. So now we've got, what happens is we've got phi 1 of this puppy. Okay, so the phi 1 stays out there, but this turns into phi naught cubed of phi naught of the previous one plus 1. So that's the plus 1 trick. So we take phi 1 of this guy instead of that. We take phi 1 of the previous one, add 1, and do phi naught cubed. And remember, phi naught is already a pretty powerful operation. It's omega exponentiation. And then we do it again. We unpack, let's see. Oh, what do we have to do? Phi naught cubed, I'm going to expand that out as phi naught squared of phi naught of something. Phi naught of something plus 1 is that phi naught times omega, because it's omega exponentiation. Now I can demote that omega to its own fundamental sequence. That becomes a times 3. Oh my gosh, but wait a minute. That expands out as that times 2 plus itself, and then it just gets ridiculous. You can stare at that for a minute and pause the video if you want. But this is already, we've got this huge sequence of phi squareds, and I'm just starting to scratch the surface of expanding out this guy. And then it's just going to get ridiculous from there. Okay, so again, this is all going to be inside the subscript slot of the F. And you can stop and do our usual thing in these videos. Stop, take a deep breath, and just try to bask in the awesomeness of how big this is going to be. It's really hard to contemplate how big this actual finite number is. This is really just a plain old, where was it? This guy, it's a plain old garden variety finite number. But how big is it? Wow. It makes the other ones that we've seen in the other videos absolutely puny, as usual. Well, what can we do now? Our usual thing has been to just barely scratch the surface of understanding one of these huge numbers and then go on boldly. Well, what we could do is we could take phi naught of 0, which is not actually a very big number, and then put that into phi that of 0, and put that in the subscript slot of the phis, and then put that in the subscript slot of the phis, etc., and use more and more nested phis. That's going to be something. It's called gamma naught. It's called the Feferman-Schütte ordinal, and it's something that if I do it again, if I do this trick of putting it into the subscript again, I don't get anything bigger. It's the first fixed point of a new operation we now have, which is take an ordinal, put it into the subscript slot of this massive, amazing thing, the Veblen hierarchy, that creates such big ordinals. Gamma naught is really, really, really big. if you talk about when you first start thinking about the fact that there's different sizes of infinities, it's hard to even think about whether it means something to say, oh gosh, that's a big infinity. This is a big infinity. There are bigger ones, and I might do further videos about those, but this is a very big infinity. Can we get a fundamental sequence for it? Absolutely. We've basically described how to do one. We just do a finite number of these iterations of putting the numbers into the phi subscript slot. So phi sub phi sub phi sub phi sub phi, etc. of 0. Okay. Oh, gamma naught, sorry, that's of n. That's the fundamental sequence for it. So that means we could look at f of gamma naught comma n. So like f of gamma naught comma 3 would be 3 of these guys. That wouldn't be a lot bigger than what we've discovered. But say f of gamma naught comma 5 or f of gamma naught plus 1 comma 5 or something like that. This is really, really horrifically big. And it's not too hard to go to gamma 1, gamma 2, gamma 3, gamma sub n, gamma sub beta for an infinite ordinal. And it turns out there's even extensions of the Veblen idea. I haven't given you the full version of it. That actually do go fairly far beyond gamma naught, even though gamma naught's a really important way station, this Feferman-Schütte ordinal. So there's extensions of this idea that we could actually go further. But once again, like we've seen before, it starts getting maybe a little ad hoc. And it turns out there's a qualitatively better idea that even goes beyond that. It's called ordinal collapsing functions. We might do that in a future video. But right now we're at the stage where if you want to be almost assured of winning the competition with your 12-year-old friend of name the biggest number, you do like f of gamma naught comma 5 or something like that. You're going to win by such an incredible amount. It's not even funny unless they've already seen this video.